All right, so we're going to finish up chapter 6 here and then learn a few reaction, or kind of starting on chapter 8, so it's not a big ask for next week. Okay, we got to finish our discussion of these these thermodynamic values here, right? And again, the most important being delta G, because delta G tells you whether or not the reaction is actually going to happen. Okay, so we talked about how a negative delta G, we call that a spontaneous reaction. We have a fancy name for that. That would be an exergonic reaction. If delta G is positive, we call that a non-spontaneous reaction, which just simply means you mix your two reactants together, nothing's going to happen, right? That reaction will not happen spontaneously. Again, we have a fancy name for that. Those are endergonic reactions. Okay? So then the last thing to remind you of from Chem 1B, which pertains to all these thermodynamic values here, is the equilibrium constant. Okay, and this is related to free energy, but let's just take a second and remind ourselves what our equilibrium constant is. This is a constant value, so every reaction has a unique equilibrium constant. Okay? When we do our equilibrium constants, it's the concentration of what over what? What do we chant to ourselves when we're building our equilibrium constant? Products over reactants. All right? Still, to this day, every time I build an equilibrium constant, I'm like, products over reactants. Okay? So let's think. Look at this equation here. Let's say that we have a KEQ that's a really big number here, 10 to the 7, right? If we look at our equation, does that mean that we're going to have more products or more reactants? If that KEQ number is really big, what's going to be bigger, the numerator or the denominator? Our products. Okay, so anytime we have a KEQ, and this is a really big KEQ, but anytime we have a KEQ that's greater than 1, we say that this is a reaction that favors the products. Likewise, what if KEQ is a really small number? Something less than 1. Then it's got to favor the reactants, right? Then the denominator has to be the bigger number. So if KEQ is greater than 1, that's a reaction that favors the products. KEQ less than 1, that's a reaction that favors the reactants. Okay, and then lastly, there is this relationship between KEQ and delta G. Okay, and we don't have to do any math with this here. But basically what this is going to tell us is that if delta G is negative, then our equation here would give us a KEQ that is greater than 1, right? And we set a negative delta G, that's a spontaneous exergonic reaction. So that's a reaction where KEQ is greater than 1, okay? This is all saying the exact same thing. A negative delta G, a spontaneous reaction, an exergonic reaction, a KEQ greater than 1. Those are all telling you the same thing. This is a favorable reaction, right? A reaction that favors the products. Likewise, if we put in a positive value into this equation here, we would get a KEQ that's less than 1, right? And we called those positive delta G's endergonic, right, or non-spontaneous. So it turns out that these are all one and the same, restatements of the same thing. Positive delta G is a non-spontaneous reaction, an endergonic reaction. A KEQ less than 1, a reaction that favors the reactants. All that's one and the same thing. All right, so like I said, we're not really going to do any math with these relationships here. What we really want to get comfortable with, and the last topic in this chapter, are these free energy diagrams. These are sort of qualitative sketches of the thermodynamics of these reactions, and we're going to see these graphs a lot. Okay? All right, so we have a graph here. On our y-axis is the free energy. Okay? And the x-axis is kind of weird. It's what's called reaction coordinates or reaction progress. You'll hear both. Okay, so if we just take a simple reaction here that we're going to sketch the diagram for, let's do our ethene, just simple small molecule. Okay. In my chemical equation, on the left-hand side, these are my reactants. So on the left-hand side of my free energy diagram, they start off at this kind of like equal energy here, where this is the free energy of my reactants. I'm trying to make this pretty. Okay? In my chemical equation on the right-hand side, these are my products. So what we see on the right-hand side of our free energy diagram, another kind of plateau here, representing the free energy of our products. Okay. I'm sorry, I gotta backpedal a little bit. I want to do a generic reaction here. We're just gonna say reactants going to products. Okay, so then our reaction coordinates here, it just tells us the free energy of everything in between, each step in between. Right? And there's always going to be a peak in that free energy before it sort of crashes back down again. Okay? So in our free energy diagram here, there's a few pieces of information that we can get. First of all, the distance between my reactants and my products, all right, this gap right here, this represents the delta G of that reaction. Okay, so in this case here, our products are lower energy than our reactants. So this would be a reaction where delta G is less than 0 or an exergonic reaction. right, so then before we move on here, I want you to take a second and give me a free energy diagram for an endergonic reaction, one where delta G is greater than 0. What would a free energy diagram for an endergonic reaction look like? Right, for an exergonic reaction, my products sat at a lower energy than my reactants. For an endergonic reaction, my products are going to sit at a higher energy than my reactants. All right, and then I'm still going to have my little hump in the middle. Reaction is endergonic, that means product energy is greater than our reactant energy. All right. So we got this little hump in the middle here. All reactions have to go through this sort of peak in energy here. Okay? This point right here, the peak on this graph, this is what we call the transition state. It's the highest energy point in a reaction. Right? And remember, reactions, they're all about making and breaking bonds, right? Your transition state is like that weird point in the middle where all the bonds are half broken and all the new bonds are half formed, right? Before all these bonds have actually fully broken or fully been formed. Right? So we can just say half broken. Formed bonds. Okay, your transition state will always be higher energy than your reactants or products, like necessarily. Okay, so then this distance here, or before I even say that, kind of how we think about these free energy diagrams in terms of the progress of a reaction is we have our reactant here, right? We are starting out with our reactants in our reaction, okay? And we want to get all the way over here to the products. But before we do that, we got to jump over this hump right here, right? So this is my reactants. I'm trying to get to my products. I can't just cut through this way. In order to get there, I'm going to have to jump over this activation energy there. Or, well, I kind of gave it away. What we call the activation energy. Okay? So this distance right here, the distance from where you're starting, which is your reactants, to your transition state, this thing gets this symbol delta G, double dagger. It's got this subscript here, superscript here. We call it a double dagger. I don't know if that's the real name, but that's what people call it. Okay, so this delta G double dagger is otherwise known as the activation energy of your reaction. Okay, so for our second graph here, our endergonic reaction, everybody draw in your delta G and your delta G double dagger, your free energy and your activation energy.
Will we use any catalysts in this class for this?
We'll be talking about that here in a second, yep. All right, so our delta G is the difference between our reactants and products. All right, so my reactants start at this energy. My products are at this energy. So here's my delta G here, this gap. Okay, and my delta G double dagger is the difference between the reactants and the transition state. Okay, again, my transition state is that max value on my graph. So here's my transition state. So my activation energy is going to be from my reactants all the way to the energy of that transition state. All right, so here's my delta G double dagger. All right, let's talk about this activation energy here a little bit more. Okay, this is the energy your reactants have to overcome to reach the product side. All right, like we said, it's like a little marble that has to roll over that activation energy hump there. So we say that reactants have to overcome this energy barrier in order to get to the products. All right, in Chem 1B, you would have done some math. For our purposes, we're not going to do any math, but we're going to remind ourselves that this activation energy is proportional to the rate of the reaction. This little symbol here, which I have an impossible time drawing, it's like half of an infinity sign. I can't do it. Means is proportional. It's like you chop off a last quarter of an infinity sign, but I can't do Okay, so let's take another reaction diagram here, another free energy diagram. We're going to always be good and label our axes. Okay, so I'm going to put down two curves here. Okay, we're going to call the blue one curve 1, the red one curve 2. And you can see that these both begin and end in the same place, right? The difference between the reactants and the products is the same. So in this case, my delta G, for that first reaction is simply equal to the delta G of the second reaction. From a free energy standpoint, from an equilibrium constant standpoint, these reactions are equal. Okay? However, you can see that the activation energy of that blue curve, that delta G double dagger, is greater than the activation energy of that red curve. So from a thermodynamic standpoint, looking just at the delta G's, these reactions will reach the same equilibrium, because again, that equilibrium constant is proportional to delta G. Delta G is the same for both of these. All right, the difference is that red reaction will reach equilibrium much faster. The rate of that red reaction is much faster than the rate of the blue reaction. So from a kinetic standpoint, reaction 2 will reach equilibrium faster than reaction 1. All right, so we get those two main pieces of information from these free energy diagrams here. Both just like, is the reaction favorable? Is this going to have a negative delta G? Is it going to favor the products? But we also get a sense of how fast a reaction is by looking at that activation energy, that delta G double dagger. All right, reactants have to jump over that barrier in order to get to the product side. The smaller the barrier, the easier it is to jump over. All right, so if we look at a reaction that we studied in this class here, so I kind of jumped the gun with that before, but now let's look at one here. These halogenation reactions. All right, everybody take a second and give me the product of this reaction. Alright, so again, just like all the reactions we've studied up until this point, this is an addition reaction, so I'm going to add a bromine to either side of that double bond. Alright, but this is a reaction that we also know the mechanism for. Take a second and see if you can't remember what the mechanism of this reaction is. So remember this one, this does not have a carbocation intermediate. This one has that weird cyclic intermediate. If it's bromine, it's got a cool name. We call it a bromonium ion. It is, right? But anyway, point being is that we know that this reaction has this middle step here, what we call an intermediate. These intermediates are these transient states. They don't last for very long at all. You can't isolate a bromonium ion. It only lasts for like, you know, a picosecond or some ridiculously short amount of time. But nonetheless, we've established through experimentation that this reaction goes through this mechanism, and that's illustrated on the free energy diagram for this reaction. All right, this reaction is a favorable reaction and from a free energy standpoint. So if I have my reactant energy over here, this reaction is spontaneous. Where should my products be? Higher or lower? For a spontaneous reaction? Lower. Lower. Okay, but because of the intermediate in this reaction here, it's not just one hump, but rather like this two-humped camel kind of deal. All right, it has this local high energy minima right here. This is our intermediate. Let me move this out of the way, actually. All right, because of that, it's got two transition states then. This first one and this second one. All right, two maxima. And thus it's also got 2 activation energies. 2 of those delta G double daggers. The first one is the energy that these reactants have to overcome. That's delta G double dagger 1. All right, and remember, we want to think about our reaction as this little marble here. All right, so the first thing it's got to do is it's got to jump over this first one here, this first hump. And now we've gotten to this local minima at the top here. Now we're sitting at our intermediate. What's my next activation energy going to be? Big or little? Now we only have to overcome this teeny tiny little hump here in order to get to our product side. Whoops, I took that with me. So my second activation energy from that intermediate is quite small, right? Just the distance between these 2 points. Whoa. Where are we? All right, so this reaction, and this is characteristic of reactions with intermediates, it takes it kind of a long time. We have this very slow rate to get to this intermediate here, and once it's there, it's going to blow right through that point and get to our product side, right? It only has to overcome that small hump to get to our products. But nonetheless, we can see that we have an intermediate in our reaction in our free energy diagram here, because we have that little local minima at the top. That represents that intermediate, that cyclic intermediate for this case here, or in the case of our hydrohalogenation reactions, the carbocation intermediate, right? So this would be a reaction with an intermediate. It's got these 2 transition states, and then again, the overall free energy of this reaction, the delta G, is again just the distance between my reactants and my products. Okay, so we can see how many steps we have in our mechanism illustrated in our free energy diagram here. To the intermediate state.
Which is the second one, and then the second intermediate state.
Yeah, so it's all like these, like, okay, these are my new bonds. It's the transition state's going to be when all these bonds are half formed and this bond's half broken, right? We haven't quite actually gotten to the intermediate yet.
Okay.
Almost never do we know what a transition state looks like.
Oh.
It just doesn't exist for any amount of time. It's not something that we can isolate and look at or anything like that. The best that we can do are these intermediates, and even then they exist for fractions of a second. Okay. All right, so we're going to talk a lot about this reaction next class, next week. But for right now, just because we're all getting good at predicting our products of these addition reactions, this is a hydration reaction. The addition of water to an alkene. Everybody take a second and see if you can't predict the product of this reaction. What functional group do we get as our product? Alcohol. So we get an OH group on one side and a hydrogen on the other, right? Okay. We could do our math using our bond dissociation energies, and we would find that delta H is less than 0. This reaction is exothermic. I'm sorry. We could do our free energy. This reaction is exergonic. Okay? But this reaction also has a really large activation energy. All right, so if we draw our free energy diagram for this reaction here, it's got like a massive hump that we got to overcome here, right? A really large activation energy in this reaction. So this reaction will happen. We will do this reaction in the lab here, all right? But how do we overcome such large activation energies? All right, there's two main ways that we do it in the lab. The first one, the easiest, is to just jack up the temperature, to just give those reactants more and more energy so that they can jump over that hurdle, okay? Increasing energy will just increasing temperature simply has the effect of increasing the energy, or rather the kinetic energy, more specifically. Of our reactants, so they can jump that activation barrier. All right, and a good rule of thumb for these delta G double dagger variables is if this activation energy is less than 80 kilojoules per mole, this reaction will simply happen at room temperature. We don't have to do anything special, just let it go. Okay? Just to be clear, because at room temperature, there already is a good amount of kinetic energy for those molecules. They're still able to overcome that activation energy. It's not like we're sitting here at absolute zero, right? We're still got reactions going on. Our molecules still have some energy. They have enough to jump over an activation energy barrier of 80 kilojoules per mole. Anything greater than that we're going to have to do at an increased temperature. Just how high of a temperature will really depend on just how great that activation energy is. All right, but let's take a look at another reaction. We talked about this one last class. If we have ethene plus hydrogen gas, that simply produces our alkane, ethane. Okay, if we draw our free energy diagram here, okay, this reaction is also an exergonic reaction, but has this large activation energy barrier. All right, we actually did the math on this one. This one has a delta H that's less than 0. It's an exothermic reaction. The problem with this reaction is that its delta S is greater than 0. It is entropically unfavorable. All right, so why does that matter? Well, if we look at our equation for free energy here, we got delta H minus T delta S. Again, delta H is negative. Oh, shit. I lied. I'm sorry. I messed that up. Ugh. You can tell we haven't done thermodynamics. Delta's S less than 0 is entropically unfavorable. My bad. Entropically. So if we look at this equation here, we have a problem. Because what's a negative times a negative? A positive. So I have this negative plus this temperature-dependent positive value. So as T increases, delta G becomes positive. So I can't just use that same strategy of jacking up the temperature in order to overcome this activation energy, because this reaction's entropically unfavorable. That won't work. All I'll do is like change it so it won't actually occur, so that this is an endergonic reaction. All right, so the other strategy that we use is to use what's called a catalyst. So this reaction here, how we get away with it is we use a palladium catalyst, and then all of a sudden this reaction happens no problem. All right, importantly, a catalyst is not consumed in the reaction. And it does not change the delta G. So this the difference between these two here is going to remain the same. What a catalyst does do is decreases the delta G double dagger, that activation energy. So it provides a new path to get from reactant to product that has a much lower activation energy. Okay, and then sometimes, not always, but most of the time, you'll also see that it does so by introducing intermediate steps. So my reaction, my free energy diagram with my catalyst here would look something like that. Right? I have a much lower activation energy. In this case, I've introduced, how many intermediates do we see in our blue curve here? Just one, all right? I've introduced an intermediate step, but now my reactant doesn't have to try to jump over this huge barrier here. It can instead take this much quicker path in order to get from reactant to product.
What is that intermediate step?
It doesn't all, well, I cannot think of one that does not. Yeah, and oftentimes multiple intermediate steps, especially if you're talking about biochemistry reactions and enzymes. Okay, so again, we got two ways of overcoming these really high activation energy barriers. We can either increase the temperature, give our reactants more energy so they can just jump over that hurdle, or we can find a catalyst for this reaction. All right, the catalyst doesn't change the delta G. All it does is decrease that activation energy, decrease that delta G double dagger variable, delta G double dagger value. Okay. All right, so we're going to go back and then let's talk about this more extensively here. We talked about this reaction. We talked about this last time, our hydrogenation reaction. An alkene plus hydrogen gas gives us just an alkane, that addition of H2. All right, but again, what actually makes this reaction practical, right, because otherwise we're going to wait forever because it's got such a high activation energy, is this palladium catalyst, PD. So what the hell is a palladium catalyst? Well, if we look on our periodic table, somewhere, there we go. Palladium's just a metal. All right, so it turns out that if you do this reaction in the presence of this chunk of metal, it will make the reaction occur on much quicker of a basis. All right, and so what happens is we have this metal, right, just this flat solid. The hydrogen gas will come and stick to that metal surface, and that will allow the palladium or the alkene to come along and react with that hydrogen stuck to the surface. Okay, so this palladium catalyst first hydrogen sticks to the surface, then the H2 gets added to that alkene double bond. All right, so here's my hydrogen that's stuck to the surface of this metal catalyst. The alkene comes along and forms a new bond with those two hydrogen atoms. Okay? We had talked about anti-additions before, where one thing gets added to one side of the double bond, the other thing gets added to the other side of the double bond. Well, that's not going to happen here because this hydrogen is stuck to this surface. So both of those new hydrogen atoms get added to the same side of that double bond. All right, so this reaction right here is another reaction that has stereospecificity. But this is not an anti-addition. This is what we call a syn addition. Meaning that both hydrogens get added to the same side of our double bond. I have no idea, because metals are weird. They got d electrons, they interact with shit. I really have no idea. But for whatever reason, it does. And honestly, how do we find catalysts? Total guess and check. Total friggin' guess and check. Let's throw this in and see what happens, right? I mean, very, very rarely are these things like intelligently designed. More often than not, we accidentally stumble upon a catalyst. It's very hard to predict whether something will catalyze a reaction. And there are a few of them. I'm pretty sure you can use platinum, and there's one other one as well that works. I don't know why. Although they do live in the same column, so there you go. Cool. Okay, so then we have to be careful about this, right? In the case of our ethene, it doesn't really matter. We just get ethane as a product. All right, but what if we use something like cyclohexene? All right, we talked about our stereospecific product that we would get if we did our halogenation reactions where it's an anti-addition. What do we think our stereospecific product would be for a syn addition? Right? For the anti-addition, they were added to the opposite sides, right? So we got the trans isomer. What do we think we're going to get for a syn addition? The cis isomer. Okay, so both of these hydrogens will be added to the same side of this double bond. Although I guess in this case, still well. Okay, so again, this is a syn addition. We have no mechanism that we have to know for this one. There's no electron pushing arrows that we have to know for this one, but we do have to know its stereospecificity, the fact that both of these hydrogens will be added to the same side of that double bond. All right, so let's just stack these two on top of each other so we can sort of see the difference here. Let's do our anti-addition. All right, I'm going to use a different reactant. And then our syn addition, we're just going to stack these on top of each other so we can really compare and contrast. All right, for my anti-addition, I'm going to add one chlorine onto one side, so I'm going to put it on a wedge. And the other chlorine on the other side, so I'm going to put it on a dash. All right, what do I got to do to this methyl group right here? That one's got to be on a dash, right? It's got to be the opposite of what the chlorine is. It's got to be pointed in the other direction. So this methyl group is now on a dash, and the other methyl group is now on a wedge. And is this a meso compound? Be careful, I do got both dashes and wedges, but importantly those chlorines are pointed in opposite directions, right? So this is not a meso compound, so I gotta be good and include them both. So move these over. for my syn addition, now when I add those two hydrogens, I'm either going to put them both on a wedge or both on a dash. Right? Because now they're being added to the same side. And again, whatever I do to those, I'm going to do the opposite to those methyl groups. All right, is this a meso compound? This one is, so I just have to include that one product. Okay, the other thing is, if I didn't want to, I don't really have to include those implicit hydrogens, right? So either putting both of those methyl groups on a dash or both of those methyl groups on a wedge, that would be equivalent because this is a meso compound. So we can just say meso, we only get that one product. All right, so again, our anti versus our syn. Now we have this new type of stereo specificity, a syn addition. All right, and the last reaction we're going to introduce this week, and this is kind of an easy one because we don't have any regio or stereo or mechanism or any of that crap. Ozonolysis reaction. It does involve ozone, yep. So this is not an addition reaction. It's going to be one of the few reactions that we learn about alkenes that are not addition reactions. So let's just take a sample alkene here. So if we treat an alkene with ozone, okay, and the conditions for this are you use dichloromethane and it has to be super duper cold, -78°C, which might seem really specific, but it's the temperature of liquid nitrogen. So we do these in a liquid nitrogen bath. Okay, what happens is this ozone chops this double bond in half. All right, and replaces it with an oxygen. So in this ozonolysis reaction here, our double bond is chopped in half. It's cleaved, and either side is replaced by an oxygen. This is one of these reactions that we're going to study that the only thing that we need to know about it are these substrate reagent product combinations. We don't have any mechanism or stereo or regio or anything like that. All we have to know is what the products are going to be, our substrate reagent product combination. All right, and in this case here, let's just note that I drew both of my fragments here, but they're identical, so I only have to draw the one. But we can note it will make two of them.
And is the third
It flies off into space doing who knows what. We get very lazy and we don't do balanced chemical equations very much in organic chemistry. We just kind of show what happens to the organic molecule. All right, so take a second. Let's do the products here of these ozonolysis reactions. All right, so for this first one, again, we're going to chop at this double bond. Boom. So that means one of our fragments is going to contain these 1, 2, 3, 4 carbons. And now where that carbon-carbon double bond used to be, there's going to be a carbonyl. All right, these are these 1, 2, 3, 4 carbons from my reactant side. But I can't forget about this one here. So I'm going to have another fragment that's just 1 carbon big. Again, where that carbon-carbon bond used to be is going to be a carbonyl. But again, it's only 1 carbon. Right, so we chop that double bond and we replace either side with an oxygen. All right, for this one we're going to do the same thing, but this is weird because it's a ring. So even though I chop here, I'm still connected on the other side. So let's look. If we take our cyclohexene here, okay, I'm going to chop it at that double bond. I'm going to replace one side with a carbonyl. I'm going to replace the other side with a carbonyl. All right, so where my double bond used to be, that's broken. Either side is replaced by an oxygen, but I'm still connected at the other end here. So now what do I have is just a straight chain with a carbonyl group on either side. Okay, so how do we draw this correctly? We want to make sure to count our carbons. 1, 2, 3, 4, 5, 6. Okay, and then on either end will be that carbonyl group. Boom. Cool. So this was already a little bit of chapter 8 here just to get started. Chapter 8 is the reactions of alkenes. We've already studied a few of them, and we're going to study a few more next week. We're going to focus a good bit on these hydration reactions here that produce alcohols. And then, yeah, actually, that's all we have left. Cool.